Hey everyone, welcome back. Today we're going deep on something that most people in the AI world have heard about, but few have actually looked inside: DeepGEMM. It's the low-level compute engine that powers DeepSeek's flagship models, including DeepSeek V3. And it's one of the main reasons those models can run so fast and so cheaply. So in this video, we're going to break it all down: what it is, how it works, and why it matters. Here's the thing that surprises most people when they first dig into large language models. The bottleneck isn't actually the AI doing math. It's the cost of moving data around. Every time your GPU has to pull numbers from memory, do some math, and write them back, that memory trip is expensive. Modern AI models are so fast at doing the actual multiplication that they spend most of their time just waiting for data. This is called the memory wall, and it's the central challenge that DeepGEMM was built to solve. So before we talk about DeepGEMM specifically, let's zoom out for a second and ask, what actually happens inside a language model when it processes text? The answer, in almost every case, comes down to one operation: matrix multiplication. This is section 1, why matrix multiplication matters. When a language model reads your prompt and generates a response, the vast majority of its computation, we're talking about 90% or more of the total floating point operations, consists of matrix multiplications. Every layer in the transformer, every attention head, every feed-forward block, all of it is essentially multiplying large tables of numbers together. The technical term for this operation is GEMM, which stands for General Matrix Multiplication. So when you want to make a language model faster, the first thing you look at is, how efficiently can you run GEMM? The traditional approach to running GEMM on a GPU has been to use pre-built libraries like NVIDIA's Kubeless or Cutlass. These are incredibly powerful, but they come with a cost. They're designed to work for every possible use case, which means they're full of abstractions and template code. You can't easily modify them to suit a specific model architecture. And every time your code calls these libraries, you often trigger multiple separate kernel launches, which means the GPU has to stop and start repeatedly, each time fetching data from the slow global memory. DeepSeek's engineers decided to throw that playbook out and write their own kernel from scratch. So what exactly did they build? This is section 2, what DeepGEMM actually is. The answer might surprise you with how elegant it is. DeepGEMM is a library that compiles its GPU code not when you install it, but at the moment you actually run it. This is called just-in-time compilation, or JIT. The whole core of DeepGEMM is only about 300 lines of CUDA kernel code, remarkably small for something this powerful. When you call DeepGEMM, it looks at the exact size and shape of your matrices, and then compiles a perfectly tuned kernel for exactly that situation. No wasted code, no unnecessary abstractions. And once that compiled kernel is cached, future calls are instant. A recent update added support for NVIDIA's NVRTC compiler, which made this compilation step up to 10 times faster than before. Under the hood, DeepGEMM uses a technique called persistent kernels. In a traditional GEMM approach, the GPU breaks a large matrix multiplication into smaller tiles, and each tile launches a fresh thread block to handle it. This repeated launching is wasteful. A persistent kernel instead keeps the same thread blocks alive on the GPU the entire time, pulling in new data tiles dynamically until all the work is done. To move that data from global memory into the compute units, DeepGEMM uses a special hardware component on NVIDIA's Hopper GPUs called the Tensor Memory Accelerator, or TMA. The TMA handles multi-dimensional data transfers in hardware, freeing up the actual compute cores to focus exclusively on doing math. There's one more hardware trick worth understanding: warp specialization, which DeepGEMM implements using a ping-pong scheduling pattern. Inside the GPU, threads are grouped into units called warps. DeepGEMM divides these warps into two roles: producers and consumers. The producer warps are always fetching the next batch of data from memory using the TMA unit. The consumer warps are simultaneously running the math on the data that was just loaded. These two groups alternate like a ping-pong match, so at any given moment, both memory loading and computation are happening in parallel. This completely hides the latency of memory access. The result? DeepGEMM achieves up to 1,550 teraflops on a single H800 GPU, extraordinarily close to the theoretical hardware maximum. Now let's talk about the number format that makes all this possible. This is section 3, FP8, and fine-grained scaling. The standard number format used in most deep learning is 16-bit floating point, which we call BF16 or FP16. Each number takes 16 bits of storage. FP8 cuts that in half to 8 bits. The advantage is dramatic. You can fit twice as many numbers into the same memory space, and the tensor cores on modern GPUs can process FP8 operations at twice the speed of 16-bit operations. The challenge is that FP8 has a much narrower range of values it can represent, which means numbers can easily overflow or underflow and become inaccurate. DeepSeek's solved this with a technique called fine-grained scaling, one of the most important innovations in DeepGEMM. Most quantization approaches apply a single scaling factor to an entire tensor. That's called per-tensor scaling. DeepGEMM does something far more precise. For activation data, the numbers that change with each input, it applies a separate scaling factor for every 128 consecutive elements. That's a 1 by 128 tile. For model weights, which are more stable, it applies a scaling factor per 128 by 128 block. By computing these local scaling factors, DeepGEMM keeps the numbers within FP8's representable range at all times, even during the tricky moments in training when values spike unpredictably. This technique was so effective that NVIDIA itself is working on incorporating this exact recipe into their standard tooling. There's one more piece of the FP8 puzzle. When you add up many FP8 numbers, rounding errors accumulate. DeepGEMM handles this by periodically promoting the running total into full 32-bit precision. Every so often, before rounding errors compound, it takes the partial result into FP32 registers, applies the scaling factors safely there, and then continues. This keeps the math accurate without sacrificing speed, because the promotion only happens as strategic checkpoints, not on every single multiply. Now things get interesting for anyone building large-scale AI systems. This is where DeepGEMM becomes genuinely different from other libraries. Section 4. Grouped GEMM for Mixture of Experts. Modern large language models increasingly use a design called Mixture of Experts, or MoE. Instead of every token going through the same giant layer, each token is routed to a small subset of specialized subnetworks called experts. DeepSeek v3 has 256 experts per layer, but only activates a handful for each token. This creates a real problem. The number of tokens assigned to each expert varies unpredictably. Expert A might get 64 tokens. Expert B might only get 3. If you run these as separate matrix multiplications in a loop, you end up with tiny, inefficient operations and a lot of idle GPU cores. DeepGEMM solves this with grouped GEMM, a single kernel launch that handles all expert computations together, regardless of their individual sizes. But there's a clever trick on top of that. Normally, you'd compute output tiles row by row. DeepGEMM instead computes them column by column. This means the activation data for a set of input tokens stays resident in the L2 cache as you work through multiple experts. This cache-aware launch ordering improves L2 cache hit rates by over 60% and delivers up to 2.62 times the throughput of a naive PyTorch loop implementation. That's not a minor optimization, that's a fundamental redesign of how MoE computation works. At the scale DeepSeek operates, thousands of GPUs across multiple nodes. Sending tokens between GPUs over the network takes time. DeepSeek built a companion library called DeepEP to handle this, using direct GPU-to-GPU transfers over InfiniBand without any CPU involvement. DeepGEMM is architecturally integrated with DeepEP. As soon as the first chunks of data arrive from the network, DeepGEMM starts computing immediately. It doesn't wait for all the data to land first. Combined with a bidirectional pipeline technique called dual pipe, the network communication time is almost entirely hidden behind useful computation. The GPU is never sitting idle. Now let's look at what DeepSeek released in early 2026, because these updates take everything we just discussed to a completely new level. Section 5, Mega MoE and FP4. The biggest update in the April 2026 release is called Mega MoE. Previously, a full MoE forward pass involved 5 separate GPU kernel launches, dispatch tokens to experts, run the first linear layer, apply Swigglue activation, run the second linear layer, then combine results. Each step had to write intermediate results to high bandwidth memory and read them back. Mega MoE fuses all 5 into one single kernel. Data goes in, gets processed entirely inside GPU registers and shared memory, and results come out without ever touching slow external memory in between. This is kernel fusion taken to its extreme, and it eliminates the biggest source of hidden memory bandwidth waste in MoE models. The same 2026 update also introduced FP4, just 4 bits per number. DeepGEMM now supports running model weights in FP4 while keeping activations in FP8, a combination called FP8 by FP4 GEMM. This was designed to work with NVIDIA's Blackwell architecture, which has native hardware support for this mixed precision format. On a practical level, it means you can fit a 70 billion parameter model entirely onto a dual GPU server. Alongside this, DeepGEMM added the FP4 indexer, a kernel that accelerates the scoring computation used in multi-token prediction, where the model tries to predict several future tokens in parallel rather than one at a time. The combination of multi-token prediction and FP4 acceleration delivers measurable gains in production. Tests on H200 GPU clusters using an Eagle-based MTP algorithm showed 1.8 times faster inference for single-query workloads and 1.5 times faster for batch workloads. This matters enormously in real deployments where you're serving many users at once, and where every millisecond of response time affects user experience and infrastructure cost. DeepGEMM is built specifically for NVIDIA GPUs, but other leading AI labs have built their own equivalents on completely different hardware. Let's compare the approaches. Section 6. DeepGEMM versus the world. Google's Gemini models run on TPUs, tensor processing units, which use a completely different architecture than NVIDIA GPUs. Instead of streaming multiprocessors, TPUs use a systolic array, a grid of compute units that passes data from cell to cell like a wave, perfectly suited for matrix multiplication. Google's equivalent of DeepGEMM is a framework called Pallas, which lets engineers write code that directly controls the TPU's memory layout and compute schedule. For quantization, Google uses a library called AQT Accurate Quantized Training, which bakes FP8 awareness directly into the training process from the start. Google's latest TPU cluster, Ironwood V7 at 9,216 chips, delivers an astounding 42.5 exaflops of FP8 compute. Anthropic trains Claude on Amazon's custom AI chips, Trainium and Inferentia, through an $8 billion partnership with AWS. To get maximum performance from these chips, Anthropic uses an interface called NKI, the Neuron Kernel Interface. Like DeepGEMM on NVIDIA hardware, NKI lets engineers write code that directly targets the compute engines inside the chip, eliminating unnecessary memory operations and fusing layers together. All three companies, DeepSeek, Google, and Anthropic, have arrived at the same fundamental insight. At the frontier of AI, you cannot extract maximum performance using off-the-shelf software. You have to go all the way down to the hardware. That's it for today. See you in the next one.